People keep repeating the same sentence. ASML said it was physically impossible. That's neat. It's memorable. It's also incomplete. Because if something truly violates the laws of physics, it doesn't quietly appear inside a production fab. Yet in 2023 and 2024, processors linked to SMIC's 7-nanometer class manufacturing began showing up inside Huawei products, despite years of increasingly severe American export controls. The restrictions were designed around a simple assumption: deny China access to ASML's extreme ultraviolet lithography systems, and the country's semiconductor ambitions would eventually hit a wall. That wall was supposed to be permanent. It wasn't. The question isn't whether SMIC somehow defeated physics. It didn't. Physics has remained remarkably consistent over the last few billion years. The more interesting question is why one of the world's most advanced lithography companies concluded that a certain manufacturing route made little practical sense, while engineers under sanctions decided it was worth attempting anyway. Those are very different claims. And the distinction matters because it changes how we think about technological competition. If the answer were simply China copied Western technology, the story would almost be boring. Governments know how to respond to copying. But if sanctions create incentives to invent manufacturing methods everyone else abandoned for economic reasons, the strategic picture becomes considerably more complicated. There's another consequence that rarely enters the discussion. Every smartphone, AI accelerator, military radar, electric vehicle, and cloud server depends on semiconductor supply chains that most people never see. If one country proves there is more than one viable path to advanced manufacturing, even an expensive one, the leverage embedded in those supply chains begins to shift. Not overnight, but steadily. One figure is worth keeping in the back of your mind: around 13.5 nanometers. That's the wavelength used by ASML's EUV lithography systems. We'll come back to that number later, because understanding why it matters explains both ASML's confidence and SMIC's strategy. The popular version of this story usually begins with export controls announced by the United States in October 2022. Washington targeted advanced semiconductor manufacturing equipment, high-performance computing chips, and the expertise required to support them. The objective wasn't hidden: slow China's progress in advanced computing, particularly technologies with military applications. From Washington's perspective, the logic was straightforward: no EUV machines, no leading-edge chips, problem solved. Except manufacturing has never been that linear. Long before EUV became commercially viable, companies around the world relied on deep ultraviolet lithography, DUV, for progressively smaller process nodes. The challenge was that as transistor dimensions shrank, DUV approached its physical limits. The industry answered with EUV because, in theory, it dramatically simplified the patterning process. Simplified doesn't mean easy. ASML spent decades and billions of euros turning EUV into a commercial reality. The machines eventually weighed around 180 metric tons, incorporated components sourced from thousands of suppliers, and projected light generated through one of the most sophisticated engineering systems ever placed on a factory floor. Building one is difficult. Maintaining one may be even harder. China couldn't buy them, so what options remained? The obvious answer was wait. The less obvious answer was make older tools perform work they were never expected to perform economically. Notice that word, economically, not physically. Those are not interchangeable. A process can be physically possible while being so slow, so expensive, and so difficult to control that every commercial manufacturer dismisses it. That's often where engineering and economics diverge. Engineers ask whether something can be done. Companies ask whether it should be. SMIC's engineers were operating under a different equation altogether. when the alternative is technological stagnation, an inefficient manufacturing process suddenly becomes far more attractive. There's a dry irony here. The sanctions were intended to reduce China's incentive to pursue advanced manufacturing. Instead, they increased the value of every additional percentage point of yield engineers could squeeze from equipment the rest of the industry considered yesterday's technology. That's not a judgment, it's simply how incentives work. But this is where the story becomes much more technical and much less comfortable for both sides. Because the real breakthrough wasn't a secret quantum machine, and it certainly wasn't the suspension of physical laws. It was something subtler, and understanding it requires looking at what ASML actually meant when people paraphrase those famous words, dot. Remember that number from earlier, 13.5 nanometers? That wavelength is the reason EUV exists in the first place. Shorter wavelengths make it easier to print extremely small features onto silicon wafers. For decades, the semiconductor industry knew deep ultraviolet lithography, operating at 193 nanometers with immersion techniques, was approaching its practical limits. The solution wasn't simply to improve DUV forever, it was to change the tool itself. ASML bet the company on that transition. It wasn't an obvious decision at the time. EUV development consumed decades of research, required cooperation from companies like Zeiss for optics and Cymer for light sources, and became one of the most complicated industrial projects ever commercialized. Every machine eventually contained well over 100,000 components. The price climbed beyond $200 million per system. Yet customers accepted those costs because the alternative, continuing with older lithography, became increasingly inefficient. That word matters again, inefficient, not impossible. This is where a great deal of online discussion goes off the rails. You'll often hear people say, ASML declared producing advanced chips with DUV was physically impossible. If you actually read statements from ASML executives over the years, the emphasis has usually been different. They argued that beyond certain nodes, using only DUV required so many patterning steps that it became commercially unrealistic. Yield suffered, cycle times increased, costs exploded. Those are engineering and economic objections. They're not statements about violating the laws of nature. The distinction sounds subtle until you see what SMIC appears to have done. Instead of replacing one exposure with one EUV pass, engineers likely relied on multiple DUV exposures to build patterns layer by layer. This approach, commonly called multiple patterning, was already familiar to the industry. Intel, Samsung, and TSMC all used variants of it before EUV matured. The difference is scale. Imagine drawing a perfectly straight line. You can do it once with a ruler, or you can draw 4 shorter segments and hope every connection is perfectly aligned. Both methods produce a line. One simply demands far more precision. Semiconductor fabrication works in much the same way. Every additional lithography step introduces another opportunity for microscopic alignment errors. Even a deviation measured in just a few nanometers can reduce yield. And yield is where semiconductor economics become ruthless. Suppose a wafer contains hundreds of chips. If 95% work, the factory makes money. If only 50% survive testing, profitability collapses. That's why leading manufacturers obsess over defect density rather than headline process nodes. A factory doesn't sell transistor sizes, it sells functioning chips. This is also why sanctions changed SMIC's incentives. For TSMC, Samsung, or Intel, spending weeks refining an inefficient manufacturing flow would have been irrational because EUV already existed. Time was better spent moving to the next generation. SMIC didn't have that option. When every advanced EUV machine was unavailable, Improving DUV wasn't merely a temporary workaround. It became the only available road. History is full of examples where constraints force engineers toward solutions that richer competitors ignore. During the Apollo program, NASA engineers repeatedly replaced elegant theoretical designs with heavier, more practical hardware because reliability mattered more than beauty. Soviet aircraft designers often simplified systems because maintenance in remote locations mattered more than sophistication. Neither approach was universally superior. Each reflected different constraints. Semiconductor manufacturing is no different. Different constraints create different engineering cultures. There's another overlooked factor. Modern chip production isn't determined by lithography alone. Deposition, etching, metrology, process control, advanced packaging, and software all interact with one another. Improving one stage by just a few percentage points can compensate for weaknesses somewhere else. Progress doesn't always arrive as one dramatic invention. Sometimes it arrives as hundreds of tiny improvements that compound over several years. That makes outside analysis surprisingly difficult. No company publishes a detailed manual explaining exactly how it solved yield problems under sanctions. Analysts infer progress from patent filings, supplier data, product teardowns, and manufacturing behavior. Some conclusions are stronger than others, so it's worth acknowledging uncertainty. I'm not completely convinced anyone outside SMIC knows the entire process flow. Anyone claiming absolute certainty should probably be viewed with caution. Even so, the evidence points in one direction. Huawei's Mate 60 Pro wasn't just another smartphone launch. Independent chip analysis found a domestically manufactured processor that very few observers expected to exist when it appeared. Whether production volumes remain limited is a separate question. The important point is that the device existed at all. That forced governments, investors, and competitors to reconsider assumptions they had treated almost as facts. But here's where the story takes another turn. Because even if SMIC proved advanced manufacturing without EUV is possible, that doesn't automatically mean China has solved its semiconductor problem. In some ways, it may have created an entirely different one. The easiest conclusion would be to say the sanctions failed. I don't think the evidence supports that. The equally easy conclusion would be to say the sanctions worked exactly as intended. That isn't supported either. Reality has landed somewhere in the uncomfortable space between those two positions. SMIC appears capable of manufacturing advanced chips without access to EUV. That is significant. But capability and competitiveness are not the same thing. One measures whether something can be built. The other measures whether it can be built repeatedly, cheaply, and in volumes large enough to reshape global markets. Those are very different tests. Let's assume for a moment that SMIC's multi-patterning process achieves acceptable yields. Even then, every additional lithography pass consumes machine time. More machine time means fewer wafers processed per day. Fewer wafers spread fixed factory costs across a smaller number of finished chips. The economics become increasingly difficult. This is where TSMC still enjoys a remarkable advantage. A modern semiconductor fab isn't a collection of expensive machines. It's an optimization engine. Every minute saved on one production stage ripples through the rest of the factory. Shorter production cycles improve cash flow. Higher yields reduce waste. Better automation lowers defect rates. The winning factory isn't necessarily the one with the smartest engineers. It's the one where thousands of engineering decisions reinforce each other. That's difficult to replicate under sanctions. But here's the reversal that deserves more attention. The sanctions may have delayed China's access to the fastest manufacturing technology, while simultaneously accelerating China's determination to eliminate foreign dependence altogether. Those objectives aren't identical. Before 2022, many Chinese technology companies could simply purchase foreign equipment and focus on designing products. After 2022, that calculation changed. Equipment manufacturers, research institutes, universities, provincial governments, and state-backed investment funds suddenly shared the same objective: replace imported technology wherever possible. Money followed. According to public investment announcements, China's National Integrated Circuit Industry Investment Fund, better known as the Big Fund, has financed multiple rounds of semiconductor development over the past decade, while provincial governments launched their own complementary programs. Some investments failed spectacularly. Others disappeared into projects that produced little beyond impressive press releases. That happens in every industrial policy. Failure is part of the cost. The difference is that China kept funding the next attempt. Western commentary often focuses on those failures because they're visible. Empty factories photograph well. Bankrupt startups generate headlines. What receives less attention is the cumulative effect of hundreds of smaller successes that never become international news. A domestic etching tool improves by 5%. A local photoresist supplier reaches acceptable quality. An inspection system replaces one imported component. None of those developments individually transform the industry. Together, they gradually reduce dependence. That's why looking only at process nodes can be misleading. A 7-nanometer chip is the final product of an ecosystem involving chemicals, software, optics, precision machining, specialty gases, wafer production, electronic design automation, and advanced packaging. Weakness in any one area limits the whole chain. China still has genuine vulnerabilities. Electronic design automation software remains dominated by American firms. High-end semiconductor manufacturing equipment is still led by companies in the Netherlands, Japan, and the United States. The most advanced precision optics remain extraordinarily difficult to reproduce. Even if domestic alternatives improve, catching decades of accumulated expertise is measured in years, not months. Ignoring those realities would be as misleading as pretending Huawei's recent processors never existed. Both narratives leave out half the picture. There's also a strategic cost that doesn't appear on semiconductor balance sheets. When technology ecosystems split, duplication becomes inevitable. Two supply chains begin producing similar equipment, similar software, and similar manufacturing capabilities. Not because duplication is efficient, but because dependence has become politically unacceptable. From an economist's perspective, that's wasteful. From a national security perspective, it can look entirely rational. That's the tension driving today's semiconductor race. I have one lingering question that I don't think policymakers have answered convincingly. If export controls motivate a country to invest hundreds of billions of dollars into replacing foreign suppliers, what does victory actually look like? Delaying progress by 5 years may be strategically valuable. Encouraging permanent industrial independence could produce a very different outcome. The answer depends on something we've barely discussed so far: time. Because in semiconductors, time compounds almost as powerfully as technology itself. And that's where this story stops being about SMIC or even ASML and starts becoming a question about the future structure of the global economy. Let quotes. Go back to the sentence we started with. ASML said it was physically impossible. After everything we've covered, I think that's the wrong debate. The real question isn't whether physics was defeated. It wasn't. The real question is whether the semiconductor industry, and perhaps policymakers as well, became accustomed to treating the most economical engineering solution as the only engineering solution. Those aren't the same thing. For nearly 2 decades, the industry's roadmap assumed EUV would become the universal answer. That assumption was logical. It reduced manufacturing steps, improved throughput, and eventually lowered costs at the leading edge. If every major chipmaker has access to the same technology, pursuing anything else looks irrational. But sanctions changed the objective function. SMIC wasn't trying to maximize profitability in the same way TSMC or Samsung were. It was trying to maximize technological continuity under conditions where the preferred equipment simply wasn't available. That's a completely different optimization problem, and engineers tend to surprise people when you give them a different objective. Does that mean China has caught TSMC? No. The gap remains substantial. TSMC continues to lead in yield, manufacturing scale, customer confidence, advanced packaging, and production efficiency. It has years of accumulated experience operating EUV at industrial volumes, and experience is one of the few things money cannot purchase instantly. ASML remains equally difficult to replace. Its dominance isn't based on one patent or one machine. It's an ecosystem built over decades alongside companies like Zeiss, hundreds of specialized suppliers, and thousands of engineers refining microscopic tolerances that most people will never think about. Reproducing that industrial network is vastly harder than reverse engineering a single piece of hardware. So anyone claiming China has already won the semiconductor race is reading the evidence far too generously. But there's another mistake on the opposite side. Assuming sanctions permanently froze Chinese progress has also become difficult to defend. What we've seen instead is adaptation, sometimes slow, sometimes expensive, sometimes surprisingly effective. History suggests this pattern isn't unusual. In the 1980s, Japan's semiconductor rise forced the United States to rethink industrial policy. In the early 2000s, very few analysts expected Taiwan to become the center of the world's most advanced chip manufacturing. More recently, governments across the United States, Europe, South Korea, Japan, and India have launched massive semiconductor initiatives because everyone has reached the same conclusion. Chips are no longer just commercial products. They're strategic infrastructure. That changes how countries calculate costs. An investment that looks irrational on a quarterly earnings report may look entirely reasonable when measured against national security over 20 years. I suspect that's the framework we should be using. Not, can SMIC manufacture one advanced processor? It already has. Not, can China replace ASML tomorrow? Almost certainly not. The better question is this: if both sides continue investing at today's pace for the next decade, what does the global semiconductor map look like in 2035? That's the competition that actually matters. My own view is that we're heading toward a world with two increasingly capable semiconductor ecosystems rather than one dominant global supply chain. The Western ecosystem will likely retain leadership at the absolute cutting edge for years, perhaps longer. China, however, appears determined to become sufficiently self-reliant that future sanctions become progressively less effective. Neither outcome is absolute. Both can be true simultaneously. And that may be the most consequential lesson in this entire story. Technology races aren't decided by a single invention. They're decided by whether a country can sustain thousands of small improvements year after year, even when progress is slower than everyone hoped. That isn't as dramatic as a headline claiming physics has been overturned. It's also much closer to how engineering usually works. One final thought. Whenever you hear that something is impossible, it's worth asking one extra question. Impossible according to physics, or impossible according to this year's balance sheet? Those answers have shaped more of modern history than most people realize. If you enjoyed this analysis, consider subscribing. We spend a lot of time separating engineering reality from political storytelling, And in a world increasingly built on semiconductors, that distinction is becoming harder to ignore.